So number 21, again, I've organized my information. I know that I have 2.45 grams of this NaCl-CaCl2 mixture. And it's reacted with AgNO3 to make AgCl. So if I'm writing kind of my net ionic here, the only thing that matters is the chlorine reacting with the AgNO3. The Na and the calcium really aren't part of this. What we have to figure out is how much chlorine we had, and then we can figure out how much was with the sodium, how much was with the calcium. So 6.127 grams of AgCl is going to be a molar amount of, I've got a molar mass of 143.35. So that's giving me 0.0427, I believe it is, moles. So what I did next is different than the solution that they provide in the e-text. I took the 0.0427 moles, and that's of my AgCl. And I know that that came from there were three chlorine ions on the other side, one from the Na and two from the Cl2. So if I divide this by 3, what I get is 0.0427 divided by 3, I get 0.0142 moles, and that's really how many moles of NaCl I have, and then how many moles of CaCl2 I have, because CaCl2 would need 2 of these chlorine, or 0.284 moles, to make up the CaCl2. So that's how I figured out how many moles of NaCl and CaCl2 I had. So then they want you to go ahead and calculate the percent by mass of sodium and calcium in the mixture. Well, now that I know how many moles of each I have, so 0.0142 moles of NaCl, when I multiply that by its molar mass of 58.44 grams per mole, I come up with 0.83 grams of NaCl, and then I do the same thing, 0.0142 moles of CaCl2, and this weighs quite a bit more, 110.98. And so this is going to be 1.58 grams. And if I add this together, I get 2.406 back. Okay, actually, instead of 0.158 here, I get 2.46. Let me back up here. Sorry about that. I get 1.63 grams here. So now when I added it up, I come up with 2.460. And that's significantly close enough. I'm okay with that. They had 2.450. So now I can go ahead and calculate my percentage out of the 2.45 and out of the 2.45. And I come up with a mass percent for each of 33.9% for the NaCl, or about 34%, and then 66% or 66.5% for the CaCl2. And again, when you add those up, you come up with 100.4%, which within the sig figs and the uncertainty, that's just fine. So number 22 tells you have this hydrate of potassium carbonate, and when it's hydrated, it weighs 10 grams, and when you heat it up and have the salt only, it's 7.93 grams. So part A wants to know how many moles of water this is. So if we subtract, we can assume the 2.07 grams that we lost was all water. Take that 2.07 grams and convert it into moles, knowing that there's 18.02 grams per mole, and that gives me 0.115 moles of water. And then B, you could do the same thing for the salt. I want to know the number of moles of anhydrous salt, so I've got 7.93 grams. And my molar mass for potassium carbonate is 138.21, or 0.057 moles. And then part C says, determine the formula of the hydrate. Well, if I look at this ratio and divide, I get very close to 2. 0.115 divided by 0.057 is 2.017, or I can assume 2. So my formula is K2CO3.2H2O, or 2 waters per formula unit of the salt. And then D wants to know, how could you determine that all of the water has been driven out of it? What you'd want to do is weigh it after you've heated it, reheat it, weigh it again, and if the mass goes down, then you lost some more water, and you'd want to keep checking until you get the same mass even after reheating. For number 23, you have two gases reacting to give you ammonium chloride, but they're not under the same conditions, so when they ask which one is the limiting reactant, or which reactant is excess and which is limiting, I have to convert these both to N. I have to find my number of moles of each using PV equals nRT. So for the first one, P is 160 kilopascals, V is 625 or 0.625 decimeters cubed. I want decimeters cubed since I have kilopascals. And then N is what I'm hoping to find. R then is 8.314, since I have decimeters cubed and kilopascals. And then my temp is 315 Kelvin. So N for my first reactant is 0.0382 moles. For my second reactant, then 113.3 kilopascals, 0.740 decimeters cubed, and 8.314, and now the temp is 330. So N for my second reactant is 0.0306 moles. So my excess reactant is the NH3, and my limiting reactant is the HCl. And then for C, they want to know what mass of NH4Cl forms. Well, since it's all a 1-to-1 ratio, 0.0306 moles is going to form, and it has a molar mass of 53.50 grams per mole, which is going to give me 1.64 grams of ammonium chloride. So number 24, when you read it, they tell you that sulfur dioxide is one of the gases associated with the formation of acidic deposition. It's released during the process of extracting lead from lead ore when lead sulfide, PBS, is roasted to form lead oxide. And you're supposed to write a balanced equation for this for part A. Well, the assumption is that since you're forming PBO, you realize roasting means heating it in the presence of O2. So I've got the balanced equation here. And then B wants to know what mass of sulfur dioxide is produced when 1 ton, and ton is TONNE. So here's another little quirk for you. This is a metric ton, which is 1,000 kilograms. So how much sulfur dioxide is produced when 1 ton of the lead sulfide is heated? So 1,000 kilograms times 1,000 grams per kilogram, that's a lot of grams. So we've got 1,000,000 grams, or 10 to the 6 grams of PBS being heated. So dividing this by the molar mass of 239.27, I've got 10 to the 6th, or 1,000,000, divided by the 239.27. So I'm coming up with 4,179.4 moles of the PBS. And fortunately, this is a 1-to-1 mole, so this is also my moles of SO2. So as far as grams of SO2, 4,179.4 moles times the SO2 is going to weigh 64.07 grams per mole. And when I multiply this, I'm coming up with 267,772.8, or 267,772, or 773, or we could just express this as 0.263 tons, or 0.268 tons, I mean. And TONNES indicates it's a metric ton. And then part C, what assumption have you made? You've assumed PBS is your limiting reactant, so that all the PBS has been consumed. So number 25, they describe a single replacement reaction where aluminum reacts with copper sulfate. So for part A, you're asked to write the balanced equation. And then B wants to know how many moles of aluminum are needed to react with 10.38 moles of copper sulfate. So 10.38 moles here They want to know the moles of aluminum. So I can set up my molar ratio of 2 aluminum per 3 copper sulfate. And when I do that, 10.38 times 2 divided by 3 gives me 6.92 moles of aluminum would be needed. Part C wants to know how many moles of copper are produced if 3.95 moles of copper sulfate react with the aluminum, so assuming that's our limiting reactant. So this is CuSO4. They want to know copper, and I see it's a 3:3 ratio. So I can also expect 3.95 moles of copper. And then finally, D wants to know what changes might be observed. Well, copper sulfate, remember copper has a characteristic turquoise or bluish color, so you would expect to see your solution go from blue to clear, or at least more clear. And also copper has a characteristic orange, so you would see an orange metallic precipitate.